All right, I just want to make a little video to show you those graphics that are a little difficult to include. So I'm going to share the screen, and it's just going to be those graphics there. You should be able to see this. This is the first graphic. It basically summarizes key elements of it. It has the Ohmic equation here, Ohm's law. This is the way it's formally presented. This is easier to remember. V is equal to IR. Vir is a word in Latin. The other important thing that you want to calculate with these kinds of circuits is the power. And it's given as the current times the voltage, and using Ohm's law, you can express it in terms of whatever you have. If you just have the current and the resistance, it's the I square R, or the voltage squared over the resistance. So there are a couple of different ways you can manipulate that formula to calculate what the power is. And that's important in a number of applications. Here's a summary of some stuff that I mentioned but didn't give you any details. You know, the main issue here that's not in the text in the answer is the dependence of the resistance on the features of the particular device that's presenting the resistance. In particular, it's proportional to the length over the area times the resistivity. The resistivity is what depends on temperature. And that's what you can use to make a thermistor, thermocouple, those kinds of devices. Use that by knowing how the resistance depends on temperature. You can measure the resistance as it changes temperature, and then from a table read off what that temperature is. These are the things I discussed in the text. This is another summary, but I wanted to include this because this has the thing that is usually an important part of evaluating circuits with resistors in it, and that's that resistors in parallel act as an equivalent resistance that adds up linearly. Resistors connected in, that's resistors in series. Resistors in parallel have an equivalent resistance that adds reciprocally. And this is where students and others often make a mistake. They calculate this number with this reciprocal and then use that number as the equivalent resistance, forgetting that it's 1 over the equivalent resistance that is given by the sum of 1 over the individual resistors in it. Then I wanted to also show you a typical problem that is given. This is sort of the archetypical problem, to find out some properties about this circuit where you have resistors, a couple of resistors in parallel and a resistor in circuit. And you could ask, for example, how much current is drawn through the whole thing and through each of these resistors. And to do that, it's a simple approach. Once you know how to do it and have done it once or twice, you find the equivalent resistance of these two, then find the equivalent resistance of these two in series, and then you find the total current, then you find the voltage dropped across each of these two equivalent resistors, and it's no problem. And I can work you through that. But I didn't want to belabor that point as much as just give you a place to see those graphics. All right.